This is a video about adjusting the design data parameters. Let's open our base file, show you where we start, and here are our inputs, and at the very bottom we have design data, and we have a number of tabs which allow us to change various options. We'll start with the first tab, which is for ultimate, so these are the factors that affect ultimate design. At the very top here we've got capacity reduction factors. These are for codes where the capacity reduction is on, the reduction factor is on total capacity, so bending moment capacity or axial capacity. These numbers are based on whatever code you've selected, so they are the default parameters for the code. You can change them if you want. A note for AS3600 users is that this 0.85 here for flexure holds true for normal ductility reinforcement. If you use low ductility reinforcement, any sections which contain that low ductility reinforcement will adopt 0.65 for the bending moment capacity reduction factor. Material factors are for codes which reduce the capacity which reduce the material capacities instead of the total capacity. Something like Eurocode. In this case, we're looking at AS3600, so we have capacity reduction factors here relevant to AS3600, and material factors are 1. If we were using Eurocode, we would find that these material factors would drop, and these numbers up here would be 1. You don't have a combination of both material factors and capacity reduction factors. That would double up on your safety factors. Okay, then we have maximum ratio of neutral axis depth for ductility. This is essentially the maximum neutral axis depth that RAPT will allow for zero redistribution. So if you have a section where the neutral axis depth is greater than that, RAPT will add compressive reinforcement to bring that down. If you choose to redistribute moments, and you can do that here in the General tab, I'll go there very quickly, and you can see here we have moment redistribution here, which is currently at 0. But if you change that to say something like 30%, then RAPT will limit the neutral axis depth to the limit, or to that required by the code to achieve that moment redistribution. And that might be lower than the this ratio here of 0.4. In fact, it will be, because 0.4 is for zero redistribution. But the point of this number here is just that this is an upper cap. So RAPT will never allow a neutral axis depth greater than this. It may limit it to less than this if you have moment redistribution of more than 0. Then we have a ductility limit for strain. And this is used in codes like the ACI code, and you can put in a limit on the strain in the reinforcement. If you put a limit here, and you also have a limit here on the neutral axis depth, RAPT will adopt the limit that gives you the most ductile section. You can then tell RAPT whether or not you should do a ductility check at the left end or right end column. And you sometimes want to ignore ductility checks at the left end and right end of the column, particularly for post-tensioned sections, and that's because at the very ends, at the column ends, your post-tensioning level is normally at mid-height of the section, and that can lead to ductility issues. But often there is very little moment at the end of a span, at the end span and at the column, and you may not be worried about ductility there. So you can turn those checks off if you want to. Maximum reinforcement limit. This is a check or a limit that is placed on the minimum reinforcement. So normally a code will require you to reinforce for at least the cracking moment and times 1.2. However, sometimes you may have a requirement where you've got a very deep beam, but it's not for any structural reasons. Say an architect wants something very deep, and you have very low moment on that beam. In that case, you may be penalised, even though it's required by AS 3600, you may be penalised into putting a lot more reinforcement to achieve your minimum strength limit. And in that case, RAPT says, well, if you want to override the code, you can put in a minimum capacity based on the bending moment in the beam. So if the bending moment the minimum number you can put in here is 1.33. So if you put in 1.33, that means that RAPT will ensure that the minimum reinforcement must meet 1.33 times the bending moment, or the largest bending moment in the section, sagging or hogging. If you have 0 here, RAPT will ensure that your minimum reinforcement meets the code requirements, which for AS 3600 will be 1.2 times your cracking moment. Okay, you can then tell RAPT whether or not you want to consider your transverse beams for critical sections in flexure. You can tell RAPT where you want the critical flexural section. A value of -1 means that RAPT will adopt the code limit. So for example, in AS 3600, the distance from the center of the support to the critical section is 0.7 times the half length of the column. Now you can change that. If you add 1 in here, it'll mean that the critical section is taken at the face of the column. You can then adjust the default side face cover. The left side face cover is the internal cover of, so the cover for internal faces of beams. In other words, beams that are within, that would likely be internal. And the right side face cover is external, when you have an external end panel or an external panel. So that would be exposed to the elements. So you might have different numbers here. RAPT uses these numbers to determine the distribution of reinforcement, or the amount of spacing you've got for the reinforcement top and bottom. Pre-stress minimum reinforcement basis. So there is a minimum reinforcement that is sometimes applied to pre-stress, particularly unbonded pre-stressed. The program default here is to provide minimum reinforcement in accordance with UBC, which is the Universal Building Code for the Western states in the US. But you can then select others if you like for this minimum reinforcement. You can select here shear enhancement at supports. If you have a load that is close to a support, sometimes you can get a direct load path from the load to the supporting column if it's not too far offset. And depending on that distance, you can get an enhancement in the shear capacity. You should refer to the guidance within the codes there to determine if it's appropriate for you. But typically, RAPT will switch this on for particular codes and turn it off for other codes. So BS 8110, the Indian standard, South African standard, these ones it will switch on for, but it will default to not on for AS 3600. And if you want to use it, you need to take a look at that fairly carefully. Similarly for EC2. The next thing you can adjust is AST value in shear calculations. So RAPT will calculate that for you. And in that case, RAPT is calculating what has been developed appropriately. Or you can tell RAPT to use the maximum reinforcing value between mid-span on either side of the support. and it will use the maximum area of reinforcement on that face in that span. And then you must make sure that that is detailed accordingly. You can limit your reinforcement strain. By default, that's switched on. So in other words, making sure you don't stretch it past its its upper strain limit. You can also include strain hardening. If you include strain hardening, then you must also include the limit of reinforcing strain. And finally, you can select the beam shear critical section location, which is normally defined by the code. So for AS3600, that's D0 past the face of the support, but you can change that to being at the face of the support if you like. Okay, that is the options we have for ultimate design, and we can now move on to crack control. This maximum service stress change for pre-stressed sections and reinforced sections is the maximum stress you are allowing RAPT, or you're requiring RAPT to design for, so that the stress in the reinforcement doesn't exceed a certain limit. For pre-stressed sections, that is defined from the point of decompression, not from, when you first apply pre-stress and you've got compression in the reinforcement. It's from decompression to the tension in the reinforcement. So when you limit those numbers, and those stress limits can be found in various codes, when you put those stress limits in there, RAPT will add reinforcement to ensure that the stress doesn't exceed that limit. RAPT will always do a crack control check anyway, but it doesn't automatically add that into the reinforcement design or its suggested reinforcement. RAPT will just give you an output, giving you suggested bar spacings and sizes to meet crack control, and then it's up to you to put those in if these are 0. So if these are 0, then RAPT won't add reinforcement in. If you put a number in here, then RAPT will add reinforcement. And just to give you an example, if I go to output here, I go to flexural design, service, you'll see here that we have a maximum bar size and a maximum spacing. Those are the maximum spacings and bar sizes required to achieve crack control. Going back to our input, the crack control that we're talking about is defined here under crack width calculations. I'll get to that in a second, but that basically sets the limit of the crack widths that that RAPT is calculating to. But the summary is, if you have 0 in here, RAPT won't add reinforcement, but it'll give you a guide as to what you need to do to achieve crack control. If you add numbers in here, limits, then RAPT will add reinforcement to meet those crack widths limits. Relative humidity, this one affects your shrinkage and creep. So if you have higher humidity, you have less drying and therefore less shrinkage and less creep. Your average temperature will affect your creep and pre-stress loss. Your pre-stress losses, you just define what code you want that to be based on, and RAPT will use the code that you've chosen under general. So if we've got AS3600 in this case, I go back here, the program default in this case will be AS3600, but you can choose another code if you want to. For your crack width calculations I was referring to above here for your maximum service stress change, these numbers here you have to put in yourself. So whatever you put in here won't affect those numbers there. You have to go to the tables, work out what those numbers need to be and put them in. But assuming you have put 0 in here and you're just getting RAPT to define the bar spacings and bar sizes as a guide, RAPT defaults to 0.3 millimeters for reinforced concrete sections and 0.2 millimeters for pre-stressed sections. So, but you can also change that to 0.1, 0.2, 0.3, 0.4 as you desire. Okay, if we look at AS3600 shrinkage and temperature reinforcement, that will determine the amount of shrinkage reinforcement that RAPT is putting in according to AS 3600, and that is according to clause 9.5.3 in AS 3600, where you can basically determine how much deemed to comply reinforcement you need to counter temperature and shrinkage effects. So it's that input there that you put in, and then you put in your degree of restraint in the primary direction to work out, and RAPT will work out the cross-sectional area of reinforcement required. The degree of restraint in the secondary direction is not used. The concrete strength gain rate, typically that's normal, but you can you can select S and R, S being slow and R being rapid. And then AC 209, you can actually add in your constant, or you can add in inputs into a formula which determines the strength rate gain. Okay, now we'll move on to deflection. So the first option here is setting the concrete tensile strength. That will determine when you have a cracked section or not. The factor you put in here is, let's say you put in a factor of X. If you have if you're using Euro code 2, then you would have X times your characteristic concrete strength to the power of 2/3. So whatever number you have in here, so let's say I put in 0.6 for argument's sake, then the tensile strength would be 0.6 times F-C to the power of 2/3. If it's for any other code, AS 3600 ACI, then this becomes 0.6 times F-C square rooted. If you have this as -1, RAPT will adopt the default value from the code. This maximum value of your effective I value on your I gross for deflection calculations, this is the maximum I value that RAPT will adopt for deflection. So if you had you had the value 1 in here, then for any uncracked sections, RAPT would adopt the full uncracked I value. If you have 0.6, RAPT will adopt the maximum value of 0.6. The reason you'd have something lower than 1 is because you have shrinkage and temperature effects which reduce your the available tensile capacity in the concrete, and so you get cracking earlier than you otherwise would. So we recommend between 0.6 and 0.7 there. Your total deflection warning limit. This is essentially just your the limit at which RAPT will provide you a warning when deflections exceed span on 250, and that's your total deflection. This is your total maximum deflection, 25 millimeters. This incremental deflection is the deflection warning that you get for deflection that occurs after transfer and after application of your SDL that is not applied, not your extra SDL. So there are a distinction between your SDL that's applied prior to installation of brittle finishes and partitions, and then SDL that's installed after your installation of brittle finishes. So this incremental deflection is a warning on basically the deflection you'll get that your brittle finishes or your partitions will see, and this is the warning limit that you are asking RAPT to highlight when you exceed. So this is span on 500 here, and we've got a total maximum incremental deflection of 25 millimeters. The initial time for shrinkage, there are two options here. You can have full shrinkage or incremental shrinkage. Full shrinkage means that RAPT will calculate shrinkage from time 0 all the way through to the time to the end of the loaded period, which is 30 years here. If you have incremental shrinkage, then RAPT will only calculate the shrinkage that occurs from when the load is applied at 10 days in this case to 30 years. So it excludes the shrinkage that occurs prior to the 10 days. You may need that option if you ever do a staged calculation. Otherwise you keep that at full shrinkage. Time of loading in days, that's the time at which you first load the concrete, has a big impact on your creep deflections. And standard time there is 10 days. Our age adjustment factor is a creep factor, which is essentially your aging coefficient. And if you want more information on that, refer to the theory section in the help, or have a look at any concrete textbook. Okay, we have our concrete strength at the time of loading, and that is automatically calculated. So if I increase this to 18 days, you'll see that that increases automatically. But you can specify that, and you can change it if you don't like RAPT's value. The loaded period in years, which is the time at which you want final deflections to be calculated. We have our tension stiffening approach, and we've got a number of different options. Our preferred method is the modified concrete tensile modulus method, which essentially takes any areas where you have a cracked section. We allow a certain limit of tension, or we add a tensile capacity at that in that zone to give you or to replicate the stiffening effect that you get from the cracked and uncracked sections through that zone. Top surface shrinkage factor. Now these two factors here, bottom and top surface shrinkage factor, they are and the same for metal decking. They essentially determine whether or not you have a shrinkage profile. So in other words, typically you'd have in a slab a uniform shrinkage profile. In other words, the shrinkage occurs the same at the top as it does at the bottom, because it shrinks. Drying can occur from the top and the bottom equally. However, if you have metal decking or some other reason why you may not have shrinkage or drying occurring on one surface, then you can change the profile so that you have more shrinkage occurring at the top and less at the bottom. This 1.2 to 0.2, that is from the composite code, and that is the options for deflection. Now we move on to earthquake design. So these options are requirements from clause 14.5.2.2 in AS 3600 to ensure you get ductile behavior in an earthquake. And for these options to become available, you need to go back to user defined, go to earthquake design, and then select whether or not you want a moderate or high risk earthquake. Those options there, the options there are based on Eurocode. So whether you have a moderate risk or high risk, those definitions are found in Eurocode. That does not put in the earthquake loads. That just tells RAPT how much ductility you'll need, but you must put in your own earthquake loads from your own lateral analysis. A moderate earthquake is a 2 or a 3 in AS 3600. High risk is a 4, or a mu, I should say, a mu of 2 or 3, or a mu of 4 for high risk. If I click on high risk, moderate risk and then go back to design data earthquake, you'll see we now have options to input here. The first one here, the minimum reverse phase capacity at support hinge, that is essentially saying that you might have a given maximum hogging moment at a support, and RAPT will ensure you have a minimum capacity on the opposite face, so a sagging capacity as a fraction of that maximum moment. The minimum support face capacity as a fraction of the support hinge capacity is essentially a minimum capacity at the face of the support relative to the maximum hogging moment, or the maximum hogging capacity, I should say. Minimum span face capacity as a fraction of support hinge capacity essentially says that whatever the maximum hogging capacity is will be applied to the span face all the way along the span face, as opposed to this one, which was just at the support hinge. And then this one here is a minimum capacity based on the maximum span, the maximum sagging capacity in the span. So those are code requirements, and these numbers are typically, they are dictated from the moderate or high earthquake risk that we selected under general. So if we change this to high risk, then you'll find that those numbers change. Our multiplying factor for minimum reinforcement calculation, and this is here set at 1.1, which means that the standard minimum reinforcement, which is based on your cracking moment, AS3600, that's 1.2 times your cracking moment, you will increase that by 1.1, so 10% more. Most codes require an increase in your minimum reinforcement for earthquake. Next section here is concrete shear capacity within 2D of a support. And most codes require or specify that your shear capacity should be reduced or ignored when you're within 2D of a support. So this is the number you multiply your concrete shear capacity within 2D of a support, and that means RAPT will design or add steel reinforcement to supplement the strength within that region. Your neutral axis ductility limit for earthquake sway plastic hinges. This is similar to your ductility limit that we specified under ultimate, where you had 0.4, but this time you're limiting it to 0.25 for your plastic hinges. Similarly, you can have a strain limit for your hinges, which is the same as what we had for ultimate, where you had a strain limit. Finally, you can determine what your shear capacity is based on. So applied shear is where you just take the shear from the shear force diagram, and that is what the design is based on, the shear design actions. Or you can do capacity-based shear, and capacity-based shear is where you take the shear is based on your moment capacity. So in other words, a factor of your moment capacity. That's ensuring that you don't have a brittle failure. So the section, after clicking capacity shear, you then have the option to adjust your section capacity multiplier and your earthquake load multiplier. This number here is essentially 1 divided by 0.85, where 0.85 is the phi factor for flexural capacity. That gives you your nominal bending moment strengths from which your shear design action is then calculated, and then RAPT will also look at your earthquake load multiplier, multiplying your earthquake shear design force by 2, and it'll then take the worst of those two. If you want more information on that, just go to section 14.5.2.2 in AS3600. Now we'll look at the inputs for pattern loads. If you have pattern loading switched on in your general inputs, I'll go back there now, general inputs, and you can see we have pattern live load on, then those options for pattern live loading are active. If we switch that off, then you'll see that under pattern live loading, these options are no longer available. So let's go back to general, switch them on, we can talk more about them. Oh, not output, back to input, and design data, pattern loading. So the first option we have here is live load pattern factor, which is 1. RAPT will pattern load the odd spans, and then it will pattern load the even spans, and it will add live load only to those odd spans, or live load only to those even spans, and the amount of live load that it adds is determined by this number here. So 1 means full live load is applied. If you have 0.7, 70% of the live load is applied to the call it the active panels that are subject to the additional load. We can then determine which of those checks we want done for pattern live load. So we can do pattern loading for ultimate strength, for crack control, and for deflections and long-term deflections. These are the defaults. If you switch ultimate strength off, RAPT will always still do a check for shear in case there's a brittle failure, and the rest is self-explanatory. And that's it for design data options. Hope you enjoyed it. Thank you.